And then I'll ask Vasily to answer. Okay, good. So the two key references that I'm going to sort of talk about are here. Jim Morrison wrote a paper in 1957 called The Study of Variability in Engineering Design. In fact, I have the paper here. This was the very last one. When he published the paper, his company bound them up in a nice brochure. And he gave me the last one he had, and I brought it with me in case anybody wants to see it. And then he followed that 41 years later. He followed that with a follow-up paper called Variance Synthesis Revisited. And in fact, he said that he regarded his first paper as a bit of a fossil because it lay in the literature pretty much undiscovered until George Box unearthed it when he did all that research on Taguchi's methods in the early 80s. And so you can sort of think of this, I'm a sort of statistical paleontologist today. So what we're going to do is we're going to dust off Jim Morrison's 57 paper and dig a little bit deeper and just see what's in it. And we're going to do a bit of work on it that Jim sort of wanted to do, but actually didn't. So that's the value of this talk. We're going to uncover one or two little features of this paper that have been lying dormant in the fossil. So we're just dusting off the fossil and finding some things about it that we hadn't already appreciated. So that's the point of this talk. So there's the paper. I've brought it with me to prove it really does exist. And Jim autographed it for me about 10 years ago. Now that's the European version of the date, which I think means that's the 6th of March, not the 3rd of June, just to clarify. Okay. 2012, so how long ago was that? 10 years, so it's quite a while ago. So that's the 57 paper, and then that's me, because the whole point of the paper was to talk a little about statistical engineering and robustness, and so that's me learning about statistical engineering and robustness. So on the left, that's just me with Jim Morrison in 2013. Jim was pretty old by then. In fact, he lived to the age of 99 and he died in 2016. So that was like 4 years after he signed that paper. And then on the right, that's me with Taguchi. I think that picture was taken in Germany, if I remember. I'm a lot younger there, obviously. That was 1989. And Taguchi passed away in 2012. So both of these guys aren't any longer with us. I am still with you, just about. So it's good to just pay homage to these guys and just spend a little bit of time talking about their work, or primarily Jim's work, actually. Jim's work preceded Taguchi's work by quite a long way. But like I say, his work ended up being a bit like a fossil, really. So it just lay there. And George Box uncovered it. And we're just going to dust off some more. We're going to dust off some more and see. That was the last time I was here at U of M in 2001. Some of you might know DJ in the middle, and then the gentleman on the left is David Cox, who also died this year, actually. So all these dead guys. So the moral of this story is don't hang out with me. So the last time I was here was about 2001 when I was still working at the Formulating company, and I gave a talk called Science, Engineering and Statistics. I can't remember where on the campus that seminar was, but David Cox encouraged me very much to write that paper up. That is not the subject of today's meeting, but I've put the reference there. So if one or two of you download it, my H score might catch up with Vasily's. If some of you download the paper, because I think, or maybe the ResearchGate score, I don't know. So I always check Vasily's ResearchGate score and just see how, because he and I, when we worked together at the Formulating company, our scores were kind of pretty much level on ResearchGate, but he's still active and I'm not really. So I think if one or two of you download my paper and read it, I might just catch up a little bit. We'll see. Anyway, so that's it for the history, and now we'll get into the paleontology. Now then, so of course, robustness, which is formulating a design that works in spite of the effects of disturbing influences, which we call noise factors, isn't really a new problem. It wasn't a new problem in 1957, and it wasn't a new problem in the early 80s when we started to learn about Taguchi's work. So my favorite robustness example in the engineering space is the problems that John Harrison faced when he was trying to invent the longitude clock. He faced a major robustness problem in solving the longitude problem, and that was way back in the 18th century. He had to design a timepiece that kept good time despite the effects of the rolling motion of a ship and fluctuating environmental conditions at sea. So the humidity and temperature, for example. So for example, his countermeasures were, instead of using a pendulum, he used a pair of dumbbell-shaped rods. Anybody that's got a pendulum clock will know as soon as you move it, the pendulum rocks backwards and forwards and the clock stops. So his countermeasure for that was dumbbell-shaped rods pivoting around their center. And he made the timepiece tick very fast, so if it missed the tick, it didn't lose too much time. And his design was also the first application of bimetallic strips that are used these days in electric kettles to make them shut off when the water boils. So I just put that in because I just think that's historically interesting, because people have been solving robustness problems for a very long time, but they probably haven't got any. The Taguchi's contribution was to put structure around solving robustness problems, and Jim's work just highlighted a very particular area of robustness, which we'll talk about in some detail. So here's the problem that he was faced with. He worked for a company in Rugby, England, and making these little transistors here, these transistors. And the idea was that you had a glass tube, and you basically make this. You have this glass tube, and you cut a piece off, and then you insert it into this what he called a top hat. And you had to do that in such a way that the glass fitted perfectly and it didn't spill over, and I'll come to that in more detail in a minute. So this was the motivation for his 1957 paper, and the company he was working for were proceeding on a new range of these metal-encapsulated transistors. And so I'm just reading the bullets here, which you can read for yourself, really. But the envelope comprised a metal disc to which the wafer would be attached, and a flange metal top hat, which is that bit there, would then be welded to the disc to complete the enclosure. And then these things were fused together to form a hermetic seal. Now, although this case study isn't recent, it goes back to 1957, I would maintain it is modern, which is why it's worth us looking at. Let's see. So there were two robustness failure modes associated with these glass beads. First of all, failure mode A there, the glass beads would crack under temperature gradients due to the differences in thermal properties of the glass and the metal of the mounting surface that was being sealed. Now, for those of you, my colleagues from the Ford Motor Company that are here, you'll know that that's called a one-sided failure mode in the language of failure mode avoidance. It's a one-sided failure mode because it either cracks or it doesn't. The other failure mode B, so at the pre-production stage, they were seeing a high failure rate experienced because the volume of the glass bead in production was too variable due to variation in the bead dimensions. Now, this is a two-sided failure mode because they can either be too big or too small, and that's illustrated in the picture below, which that picture actually, that sketch by Jim, was from his 1998 paper. So there's more detail in the 98 paper because Jim himself was dusting off his own fossil. So there's more details in the later paper. So all I've done is just dust off some more debris from the fossil. So that's all I've done, really. And so so the noise factors there I've just highlighted in yellow. So in that first failure mode, the noise factor was temperature, and in the second failure mode, the noise factor was causing the failure mode with the variation in the bead dimensions. So the countermeasures for those were for failure mode A, the cracking, formulate the glass to have the same coefficient of thermal expansion as the metal it was sealing. And that's a pretty clever countermeasure, really. We could write a paper just on that, but Jim wrote a paper basically on the countermeasure for failure mode B, and that's what we're going to talk about. So the countermeasure for the too much variation in the glass was to minimize the effect of dimensional variation of the glass volume, and that was the main focus of the 57 paper and is the subject of what eventually I will talk about. So production of the glass beads. I did have a video loaded because I haven't preloaded it, so I think we can watch the video offline probably. But there's a still from the video there. I didn't know whether people knew what it was like to make glass beads, but basically what you do is you melt some glass and then pull out a long extraction, and you end up with a tube of glass, which you then cut to length, which is that little graphic there that I showed earlier. And this is verbatim from the 98 paper. Jim didn't include this detail in the 57 paper. But to summarize those bullets, I won't read them out because you can read them as fast as I can talk to them. But if you summarize those bullet points, this was a very manual process. People were pulling glass and walking away, and somebody was fanning it with a piece of card to keep it cool. Absolutely no control whatsoever. So it's hardly any wonder that the beads were so variable. I suppose that's the punchline, right? So that was the problem that Jim was faced with, is how do we deal with this and reduce the variability in the volume of glass? So let's have a look at the volume. So here's the glass bead, and so the volume of the glass in that bead is just the difference between the volume of two cylinders, actually, where the second cylinder is just the bore in the middle. So there's the volume. So D is the outer diameter, B is the bore diameter, and L is the length. So that's the volume of glass that you will find in that construction. And there are three design variables here, we might call them. There's D, B, and L. You can choose as the engineer what your nominal value for D is. You can choose what your nominal value for B is, and you can choose what your nominal value for L is, subject to those things combining to give you the right volume. But within that constraint, you can choose. So that's why we call them design variables. And so variation in one or more of these will transmit variation to V. And this is a well-known variance transmission equation. We've got three variables, and you square the gradient of volume at that particular variable, multiply it by the variance of the variable itself. That works if the design variables are independent. And of course, the sharp ones among you will straight away say, there's no way these three are independent. We will come to that in a minute. So obviously what's happening here is that little graphic in the bottom illustrates what's going on. So the variation that gets transmitted from the input variable to the on the x-axis to the y is simply a function of the gradient of the function at that point. So that's pretty straightforward. We've just got three of those, not just one as I'm drawing there. So here's some data that is in Jim's paper. I tried to get hold of the original data. I mean, after Jim had passed away, I actually wrote a note to his family and said, do you happen to have in Jim's files this data? But they had a look, but they couldn't find it. So I can't get to the raw data actually, which is a shame. So anyway, this is the data. What in his paper, Jim had a sample of 30 what he called standard war beads, which he measured prior to doing his investigation. So he had the average for D was 1.69 millimeters, and B was 0.625, L was 1.92. That gave a volume of 3.72 cubic meters when you plug it back into that volume equation. And then the sample variances are given in the right-hand column. Now to the uninitiated, which basically was Jim's work colleagues before he did this study, was if you said, well, if we've got to tackle variability, why don't we go after the variability in the length? Because the variability of the length, which is here, is greater than the variability of all the other two dimensions. So to the uninitiated, you might say, let's go after that. And that's what people were going to do. But luckily, Jim figured out that wasn't necessarily the right thing to do. And we'll see why in just a minute. So because I can't get from Jim exactly what the conditions were in terms of what they were trying to do in terms of actual nominals for these pieces, I'm going to assume that the target for B is 3.72 cubic millimeters, simply because that's what he saw in his 30 pieces. So we're going to say on average the beads are okay, and I'm going to treat D bar, B bar, and L bar, which are the numbers in the middle column. We'll take those as the initial nominals, and we'll just see if we can improve the situation from there. So that's what we're going to do. So we can apply the variance transmission formula. Now we've got some data. So I've tried to space it out so you can kind of see what's happening. So there's the first bullet point is just at the top there is just that equation written out. That's what we've got to calculate, and then I've put the actual derivatives in on the next line, and then I've replaced sigma d squared with the observed sample variances in the next line. Okay, that's all I've done there. So then you end up with a total variance contribution of 0.0617. Note the units, millimeters to the power 6. That's always a good question to ask students. Give me a physical quantity that has units, millimeters to the power 6. And the answer is the variance of the volume, right? So that's a good question to test students with. Well, maybe. It's very important to understand your units, isn't it, in engineering problems? You've always got to have consistent units. That's very important. So we observe. So let's just. I think I've got some builds here. To the uninitiated, I say you might go after L because that's got the biggest sample variance, which I've just highlighted there. But then when you go to the line below it, what you really find is that D that has the diameter has the largest contribution. That's contributing about 0.03 to this 0.06. That's about a third, half the variation is coming from D. Half the transmitted variation is coming from D. L is hardly doing anything really. And B is hardly doing anything either. All the action is happening in the diameter. And if you draw the surface in the DL domain, you'll see why. So that's where we're starting. And you can see the gradient in the D direction is pretty steep, but the gradient in the L direction is very flat. And that explains why L doesn't, even though L is very variable, it kind of doesn't matter because the gradient is so shallow. So that's the main. And the reason I like this case study, it's great to do this talk. It's a good excuse to come from the United States to see some friends. That's one good reason to do it. The other good reason to do it is when I teach engineers this stuff. The point is that if the intuitive solution on a problem this simple is wrong, just imagine how your intuition would hold up by tackling more difficult problems. So that's the main teaching point of this from an engineering standpoint. That your intuition will even go wrong on very simple problems. And so that's really the main teaching point when I teach this to engineers. So the consequences of all that, and again, there's a lot of bullet points here. I'll summarize them verbally. So before Jim had done this, the company was planning to spend a lot of money on a machine to reduce the variation of L, because to the uninitiated, that looks to be the right thing to do. But because it turned out that D was doing most of the work, Jim came up with a very nice control plan, because what he figured was, if you take a long tube of glass, variation between neighboring pieces of the glass is very small. So what they did was they cut the longer tube into something like 10 centimeter pieces, and then cut beads from a narrower section. So all of those beads would have a very similar diameter, because there's hardly any variation along the length of a long tube. And so then they just sorted them into batches, and that didn't need any new equipment at all. So not only did they get to the right answer here, they didn't need to spend money on a complicated piece of equipment. And there's another lesson to be learned there. How much equipment do we buy to control variation that might actually be unnecessary? That's a question to my colleagues still in the full motor company. The example really nicely illustrates the importance of careful analysis of the objective function into making the right engineering and manufacturing decisions to avoid the unnecessary cost. But so even in this mathematically simple case, the intuitive solution is wrong. So I haven't said anything yet that isn't in Jim's paper. So we haven't got to the dusting off of the fossil yet. We're getting to that. So before we get to that, let's talk quickly about the 3 stages of engineering design, because then this cues us up really. So the primary design activity in engineering is selecting the design concept to deliver the engineering objective. The secondary design activity is choosing the nominals of the design variables to achieve the objective target. And if this activity also includes choosing the nominals to simultaneously minimize the transmitted variation from the design variables to the objective function, in this case V, the volume, then Taguchi called this parameter design. That's what he meant by parameter design. Now, Jim didn't discuss parameter design in his 57 paper, but if you read it carefully, you'll see that he actually did think about it, even though he didn't do it. So this is where I step in. I'm going to do the parameter design study that he hinted at but didn't do. So that's my contribution to excavating this fossil. So if you read this, in grey there, that's the verbatim from the 50s. So what he said was, in situations in which bead volume is a critical factor, the designer can use this analysis as a guide in determining the most suitable proportion of bead for a given application. In other words, he thought about parameter design, but he didn't actually do it. So, and then finally, tertiary design, the third phase, is determining the appropriate tolerances around the nominals for the design variables, which will also help reduce variation transmitted to the objective function. Now, Jim called that variance synthesis. That was a phrase, I think he didn't coin that in the 57 paper, I think he coined that in the 98 paper. He called it that just to differentiate it from the analysis of variance, I think is why he called it that, just to emphasize that it's actually different. And Taguchi called that tolerance design. So that's just a little bit of a history, just a little bit of a look-see on what the stages of engineering design are. So what we can do now is we'll do the parameter design that Jim hinted that he realized could be done, but he didn't. So that's what we're going to do. So we'll just write down the problem now. I'm going to call this analytic parameter design. For a lot of you that perhaps came across Taguchi when I did, I'm going to say recently, in the early 80s. Now, to me, that's recent. I know it's only 40 years ago, but I can remember first about learning about Taguchi, and I met him in the, well, as you saw from the picture, in the late 80s. Now, Taguchi, when he came on the scene, encouraged everybody to do experimental parameter design. That is to say, let's do an experiment and figure out what the parameter design solution is. We don't need to do an experiment here because we know we've got the objective function in mathematical form. So I'm going to call this analytic parameter design. So the parameter design problem for the glass beads is to minimize the transmitted variation, which is given by this equation, subject to the volume being 3.72 cubic millimeters. So that's our, it's a constrained optimization problem, really. So that's what we're going to do. We're going to make some assumptions. Let me just refresh here. Digging up fossils is 30 minutes. Okay, so what are the assumptions? We're going to assume initially that the design variables D, B, and L are independent. They're going to vary independently. No way of thinking, but we'll make that our initial assumption. The variation in the design variable could be linked to its mean. In other words, the standard deviation of the design variable could be proportional perhaps to the p power of its mean. In other words, if you adjust the mean of something, its standard deviation will change as well. And that's a thing that happens very commonly in engineering applications. In fact, People's one is often you'll find in practice. So I'm going to initially assume that P is 1, which we often find in practice. That is, in statistical terms, that just means we've got a constant coefficient of variation for that variable. But there are some constraints. First of all, the bore, and again, I've had to assume this because Jim doesn't get into it in his paper, but I'm going to assume for the purposes of the analysis I'm about to do, that the bore is going to have a diameter between 0.6 and 0.65 millimeters. I'm just going to constrain it to that envelope. That will then allow the wires of the transistor to pass easily through the bore. And then I'm going to assume, well, B obviously has to be less than D, right? Has to be. And D is I'm going to assume that D is less than about 2 millimeters. And again, I've made that up. I'm just saying that seems to be like a reasonable constraint based on the data from the 30 beads that we saw a wee while ago. So, I mean, we can, in fact, I'll talk about adjusting these constraints later because those constraints turn out to be quite interesting. So those are the assumptions, those are constraints. And what did I do at that point? I decided I wasn't a good mathematician to solve that if you were a good mathematician, you could just solve that algebraically straight away. I'm not a very good mathematician, so what I do is I get my favorite computer tool out. In the first case, it was the solver program in Excel, which every engineer knows how to use, basically. So this is a freebie when you're teaching it. I mean, so I've just set that up in the Excel solver. So all you do is you start with your initial conditions, which are here. These are the nominals that we're assuming where we're starting. The target is the 3.7 through. You throw that into the solver. It then cranks. You can. I don't know whether which one you can choose which solving method you want there. I'm not sure if that was the one I actually used. That's just a screen dump. And then you run the solver. You hope it converges to a solution. If it doesn't, you then have to find a mathematician that can do it algebraically, presumably. So but if this is a well-conditioned problem, so this is going to work, right? So you crank it through the solver, and then what you find is you end up with some new nominal for and notice that the volume is still 3.72. Now, the neat thing about those nominals compared to where we started is the transmitted variation has been reduced from about 0.06 down to about 0.05. So we've reduced the transmitted variation by not dealing at all with the variation in the design variant. So that we've reduced the variation by about 14% in doing that. And that gain is equivalent to about reducing the variance of D by about 20%. We haven't reduced the variance of D by 20%, but that reduction is equivalent to doing that. So we've actually achieved that without doing anything to change the control plan on how we're currently making the beads. So that just illustrates the power of parameter design, I guess. And then on this, what I've done here is I've sketched what's going on. I've now switched from Excel to R because that's what I did. I'm a bit agnostic on computing. I just use whatever I think is going to work for the slide I'm about to do. So I flipped from Excel to R just to prove that I'm versatile.
Statisticians are much happier now.
Yeah. So if I'm giving this talk at the Royal Statistical Society, everybody breathes a sigh of relief. You can use R. Yeah, that's fine. So that's what I've done here. So anyway, what you can see there, and I'm just drawing it in the D and the L domain. I think you saw from the B isn't doing, the Bohr dimension isn't terribly interesting. So I'm just drawing this in the D and the L domain. Now the blue curves that you can see there, they're contours of transmitted variation. The red line are all the beads that I have. If you're on that red line, you'll have the target volume of 3.72. Now I've fixed B here at 0.6, I think. Yeah, I fixed B at 0.6 to draw that picture, and that's where we started. It's slightly off the red line because initially B wasn't quite 0.6; it was a little bit bigger. So that the initial starting point is slightly off the red line, and then then that's the parameter design solution, and you can see why. You see, because if you go along this red line, you're going down the hill and you're getting to numbers that are less than where you started. So that's the optimal parameter design solution there. Now, what's interesting there is now notice that we butted up against the constraint on D. That's okay. So the obvious thing to say here is what would happen if we could actually make the top hats a little bit bigger and have a bigger diameter? The answer is you can get a better result if you can do that. So the other point about parameter design here is we can look at a constraint and say, I wonder if we can actually break that constraint by changing the design of the top hats. So that would be, in practice, that would be something else you could do. So that's, and you can, so the optimal values are given there, and we've got a transmitted variation of 0.0529 millimeters to the power 6. So that's what we've ended up with. Now all of that assumes that P equals 1. That is to say, I'm assuming that the variation in the standard deviation of the design variables varies in proportion to its mean. Let's have a look what happens if we change our assumption to P equals 0, i.e. there is no dependence now. And that does interesting thing, it kind of changes the orientation of the contours. And not surprisingly, it changes the result. So at least this illustrates that assumptions are really important here. And so this is again where we've started. This was the optimal solution we had when P equals 1. This is the optimal solution under P equals 0. which is very close to where we started. Now, I suspect, although I don't know, that Jim knew this, because when P is equal to 0, the analysis is quite easy because you're not assuming that the variation is changing with the mean. And if Jim had done that, he might have said, well, because the optimal solution is very close to where I'm starting, it's probably not very interesting. And I suspect, I don't know, as I say, but one suspicion I've got is that Jim actually knew that, which is why he didn't push the analysis of his parameter design. Because when P equals 1, things are more interesting, but then it gets a lot harder to, particularly if you haven't got access to high-power computers, which he probably didn't have in 57. So this might be a reason why he didn't pursue the parameter design. But again, that's a pure guess. So anyway, you can see there are some changes here. So the nominal for D changes, it goes down by about 0.26 millimeters. B doesn't change, and then L, the length goes up by about 0.47. And in this case, the transmitted variation is higher now than it was before. So in summary, this assumption is pretty important. There's another assumption we've made, or I made, which was to suggest that all of the design variables are independent. Now, Jim indicated in his paper, in the 57 paper, that there was a slight correlation, his words, between D and B. Now that makes sense. Between the diameter and the bore, if you make the diameter bigger, I'm assuming the correlation is positive. You make the diameter bigger, the bore is going to be bigger because you're pulling these glass tubes out and so on. I can't get hold of the 30 data for the 30 beads, even though I tried. So we can't estimate the correlation from the data. All that happens, though, is if you've got correlation between variables, the variance transmission formula gains an additional term due to that correlation. I've given it there. This is this term here. And of course, this is now just the cosine rule for variances. That's all this is, because the vectors are just not at right angles anymore. So this is just the cosine rule of variances. So we add the term on and we end up with a variance transmission formula there, which is the same up to there. And we just add it on this point here, where rho BD is the correlation between, in this case, B and D. So what I've done there is just sketched out what happens if you investigate the effect of this correlation. I'm going to assume that we're going to just vary it between 0 and 0.3, and I've just done it here in increments of 0.1. And you can, when we take P equals 0, which was the last analysis I did, you can see what happens. As the correlation increases, the optimal value of D increases from 1.74 up to 1.8. And then the optimal value of B stays the same at 0.6, and the length, the optimal value for the length decreases. And there's a contribution to the transmitted variation due to this correlation of about, you can see that there, for every 0.1, I'm getting an extra 0.0018 of transmitted variance. And then when P equals 1, the correlation doesn't affect it does affect the amount of transmitted variance, but it doesn't affect the changes in the nominal. So that's the effect of the correlation. When P equals 1, there's a little bit more variation due to the correlation. So at this analysis, we're really getting down with our fine brush now, dusting off this fossil. We're just finding things that are there that are maybe worth looking at. So that's the summary when the correlation is varying between 0 and 0.3. I just took that as what slight correlation. Anything more than that is quite a strong correlation. So that's my interpretation of a slight correlation. And just one other treatment of this problem, which I'm not going to pursue tonight, basically because I haven't sorted this out in my own head yet. But I talked a little bit about the importance of understanding dimensions. And I've been quite interested in applying dimensional analysis to statistical problems, if only because you can use dimensional analysis to reduce the dimension of the total problem. And of course, you can scale things better if you're working with dimensionless units, things like Reynolds numbers and stuff like that. So that, again, engineers find this attractive. So I've got here three dimensionless variables. Pi 0 is just v over L cubed, so that's obviously dimensionless. Pi 1 is d over b, likewise, and pi 2 is b over L. And if you just do a little bit of algebra, what you'll find is that pi 0 is proportional to this. So the point is, in here now, I've reduced the problem I've reduced the objective function from 4 variables down to 3. So that's entirely consistent with Buckingham's pi theorem, which is a key theorem in dimensional analysis. That goes back to even before Jim's paper, 1914. So that's even more of a fossil. That's another fossil that I would encourage statisticians to dig out and dust off, because reducing the dimension of the problem can be very helpful. It makes the robustness problem in this case a little bit more tricky, because this no longer has a fixed target, of course, because the length is changing all the time. So it doesn't help so much with the transmitted variance problem, but it does deal with the correlation between D and B, because now we've just reduced that to one dimensionless variable, which can also be used to eliminate interactions between design variables in other situations. And the choice of pi variables isn't unique. And if you read my paper, I actually chose a different set there. So that's just a quick sojourn on dimensional analysis, not particularly relevant to this fossil, but it's worth knowing. For any statisticians that are working in engineering, you really need to know how to apply Buckingham's pi theorem to reduce the dimension of problems. And there are one or two papers in the literature about that, but modesty prevents me from telling you what that is. But if Vasily will tell you, and then my score will get even closer to it. So that's just a quick side visit on dimensional analysis. That's just a bonus. It doesn't really help us tonight. But so finally, you'll be pleased to know, how are we doing for time? We're in good shape? Okay, finally, or a final analysis, doesn't mean it's the final slide, it just means we're getting close. So in the 57 paper, Jim, he gave it dimensional data for DBR on 3 types of bead, and I've only looked at the standard wall bead. But when you look at all the data in his paper, you find 1 or 2 interesting things. For example, you can draw a plot between the mean and standard deviation of all the beads he makes in terms of diameter, bore, and length. And what you find, there's only 4 points on it, or sometimes only 3 points on a plot, so there's not a lot of information here. But it looks to me like there isn't much evidence that there's any relation between mean and standard deviation for D, and there isn't for B either. Maybe there is for L. You know, as you increase the length, the standard deviation does go up. I mean, it's not a perfect proportion, but it does go up. And for B, you can see as you increase the mean of B, you do end up with more variance. So those plots, they suggested to me that maybe a hybrid assumption would be worth looking at. That is to say, P equals 0 for D and B, and P equals 1 for L. So for L, there is a functional relationship between variance and mean, but not for D and B. So that's really maybe the last thing to look about. So I've done that here. This is the parameter design solution under the hybrid assumption. And you end up with the same selection here because D is butted up to its constraint. But what's interesting is we've now got a variance that is the lowest we've seen yet, 0.044. So this sort of highlights the point that the analytical parameter design solutions are very, very sensitive to any link that you might have between the mean and the variance of the design variable. And of course, in practice, before you implemented that on the shop floor, you would need to check that quite carefully in the laboratory. You know, are the values we're choosing for P correct? And if they are, can we replicate it in production to deliver the analytical solution? So there's always that confirmatory step to do, which I won't be able to do. A, Jim is dead, and B, this factory was knocked down decades ago. So there we are. So that's a quick summary of the hybrid solution, just allowing the correlation to change. I haven't drawn any pictures for the different correlations, but what the correlation does, it just makes the contours shift to the left a little bit. So it just moves the surface over. So that's why I haven't bothered to draw them, but that's what it does. So I think I've summarized everything there. So that's assuming that rho is equal to 0. But as rho increases up to 0.3, those contours just move to the left inside their plot. But the plots pretty much look like that. So those are the three plots that we've done. P equals 1 for everything, P equals 0 for everything, and then take P equals 0 for D, 0 for B, and 1 for L. So those are the parameter design graphs for the three scenarios we looked at. So I'll just finish finally by just a few remarks, really. I mean, Jim's paper was probably the first paper to formulate the idea of parameter design. It was certainly around long before, I think Taguchi started publishing stuff in the early to mid 50s, I think, mostly in Japanese, which is why we didn't get hold of it until the early 80s. But Jim's paper was sitting there and not being picked up, possibly because he published it in a journal that engineers don't usually read, which may explain why his ideas weren't picked up in the engineering mainstream until Taguchi's work became better well known much later. Now, latterly, I think Jim referred to his work as statistical engineering in his '98 paper. And we use this method in the Ford Motor Company, I think we still do, and Vasily and I used to teach this stuff regularly as part of a coordinated strategy to embed robust design into engineering practice. Now, in the '98 paper, Jim laid out an 11-step process for reducing variability in engineering design. Now, the final step was, this is my italics, the possibility of experimenting with the nominal values of the design parameters can be explored. This is my italic now, especially if the variances are not constant, but alter with changes to the nominal value. So that's why I've spent quite a lot of time. So Jim was hinting there, when you find my fossil, this is where you've got to get down and dust off the debris, because this is quite an important thing to look for. So really the purpose of today's talk was to recognize and honor the importance of Jim's paper as a foundation for statistical engineering, and to conduct the parameter design study that he envisaged but didn't do. And my main regret really is I didn't do this while he was still alive, and I could have shared it with him, but I didn't. So that's really why I'm sort of talking about this paper. This is the third time I've delivered this paper, and it's just making sure that Jim's fossil is recognized for the importance that it really does have in the firmament of statistical engineering. In fact, there's a lot going on, so if you'll indulge me for 2 more minutes. One of the things I'm trying to do is put together a statistical engineering group. I've got a group going on in the Royal Statistical Society. What do I mean by statistical engineering? Well, that's the definition of engineering that I like from ABET, the profession in which a knowledge of the mathematical and natural sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize blah, 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 economically, the materials and forces of nature for the benefit of mankind. What I like about the ABET definition is it clearly shows the interplay between induction and deduction, again, which most statisticians understand. So what's statistics? The branch of science that deals with inductive inference in the presence of variability. Now, I know there's a bunch of people who are into causal analysis, and that's your next talk. So I don't want to get into that. But that's my definition of statistics for what it's more. There's another plug for that same paper. And if I don't catch up with Vasily now, it's not for lack of trying, right? So what I've done back in the UK is I've set up a special interest group inside the Royal Statistical Society to look at statistical engineering. If I make the slides available post-talk, Chris, I'll give you a PDF. There's a link there. There's an email address. However, you'll be very welcome to get involved with our group. There are some groups a little bit closer to home. Jeff Vining at Virginia Tech has set this one up, the International Statistical Engineering Association. Right, I'm giving a talk to them next month on a different subject. So there's a lot, and then I think Jeff Wu is involved in this thing, an international conference on the interface between engineering and statistics. So there's a lot going on in the space of statistical engineering. And I think if Jim was still alive, he'd be very happy that finally we've got our act together and we're doing something. And so I'm just chairing a little group in the Royal Statistical Society, but I hope I can connect our group to the work that's going on this side of the Atlantic. If nothing else, it'll give me another excuse to come back, I guess. Anyway, that's sort of the last bit really, so I'm going to finish there, and I'm happy to take questions. Who's MC? Two hands.
You can be.
I'm not MC.
Well, I'm happy to MC, so I think the person at the back had their hand up slightly first.
Yeah, my question about the formula for the volume of the bead.
Yeah,
Intuitively, I would have thought it would be pi times the quantity R1 squared minus R2 squared times the length. Could you explain where the 4 in the denominator comes from, please?
where the 4 comes from. What's the equation for the volume of a cylinder? Is it pi over 4?
No, it's pi r squared times length. And since r is d over 2,
There you go.
then you raise it to the second power.
Yeah,
So
there you go. Thank you, Mr. Yes, I'm using the diameter, not the radius.
Yeah.
See, I knew the vicinity would answer.
well, remember, Tim used to be my boss. I think you're ready. I look something, I got you ready with the answer. And that's how we maintain over the years.
Yeah. I've been working on, I've just forgotten this stuff. You know, I once I knew this, but then you write these things down and you forget. So thank you.
Yeah, no problem.
All right. Yes, sir. Go ahead.
I was curious about the edge condition on D.
Yeah.
And thinking about the implication if there's a physical constraint, an engineering constraint on D, because you optimize the variability in the volume,
Yeah.
but then you're bumping up
Yeah.
against a constraint. And
Yeah.
how do you, because that, as a physicist, I would say, you're going to be getting, but I don't remember if that was a physical constraint. If
Well, I'm just assuming that the diameter of the top hat is 2 millimeters, right? So,
so then you're
so if you make a bead that's bigger than that, it won't fit.
exactly. So if you're right at the edge condition, then you're subjecting yourself to risk of D
Yeah.
being too close and
Yes, but
And not
yeah.
work.
So what you might want to do in practice is pull back by 3 sigma or something,
okay, all right.
just to avoid that.
Yeah.
But I guess what was, if you did make D, obviously if you made D bigger, then you could take more, you'd have to make the target for V bigger, because if you make D bigger, the volume that you're trying to fill has gone up.
But I'm considering the top hat to be fixed and
Yeah.
having to, that's.
Yes, so it's the edge conditioning.
Right.
So even, however, you're doing an optimization problem, once you let people know about the edge condition, they can plan for the next design.
Well, they could have even changed for this probably, because I don't think it takes much to fabricate a top hat, to be honest. And it all depends on, because in the end, these all get mounted onto a wafer, which is part of the circuit board. So see, what's cool about this sort of stuff, you do this analysis and then you start asking questions that then you think, you say, I wish I'd been there while we were doing it. And all this is the iterative process of improving design using statistics, which is why me and my former colleagues are very keen to continue teaching this stuff, because it's
The quick rule of thumb that you gave out was really helpful to just say back off by,
Yeah, I mean,
and that'll sum you, for
just
getting-
back if the sums are too difficult, the answer is 3 sigma, I think, right?
Thanks.
Yeah.
There's a question online from Keith. In general, has there been any checks made between variance transmission results and actual statistical ones, say via Monte Carlo?
Well, I don't think we need to, I mean, Monte Carlo is going to give you the same result here, because the maths is pretty well understood, I would argue. Certainly in a more complicated problem. I mean, I guess I'm probably from the generation of statisticians that was taught when if you had to resort to Monte Carlo, that was kind of admission that you weren't good enough. You want to be able to work out the variance transmission yourself algebraically. I mean, I did give up on the mathematics. If you were a good algebraist, you could have probably solved that problem algebraically and not gone anywhere near a computer, possibly. So I don't know if that answers the question, but in this case, I wouldn't expect the Monte Carlo simulation to do anything different to what I've shown analytically. Just because the problem is pretty well defined.
And Tim, I think, and maybe that gentleman asked that question is under assumption from Taylor expression, which is that you take the linear term.
Yeah, I mean,
More complicated like a car and the trucks, right? So then you have to do the simulation or whatever, or an estimate.
Yeah, well, when there's complicated relationships between the variables, it's hard to analytically solve. That's.
Yeah.
So that's what Monte Carlo is.
Yeah,
Well,
yeah. But if you're hardcore, you try and solve the maths first, right? Anyway. Yeah, go on.
So the countermeasure, my understanding was to make smaller batches, right, to reduce the variation?
Yes, that's what they did at the time, yeah.
How did they then control the variation between the batches?
They didn't need to because, they just rely on the cut length. If they measure the diameter, they can work out, they know what the bore is, they can work out what L needs to be. So you take a batch. And then you think, okay, this diameter is slightly bigger than the last batch I had, so we need L to be a bit less.
Okay, that
Yeah,
makes sense.
so that's
Carry
kind
the
of what I
calculate
did.
based off.
But it was a very good control plan because all it needed was a little bit of more care and attention by the guys cutting the pieces. I
you
think.
just can't cut too close to the end, because that's where the diameter is going to be changing.
Yes, exactly. Yeah. Yeah, I had a video of somebody drawing a glass tube, but I didn't set it up. And if I play it now, you'll just get all the ads on YouTube because I haven't signed up for the ad-free version of YouTube. But you can just get, if you go onto YouTube, you can see the little video on how to make glass tubing. If you're interested in replicating, that would be a great student project. We could replicate Jim's.
Did you say you had the link in your slides?
Yes,
Okay.
it's hidden though. It's on. It's just been. I've just got a hidden.
No, I'm just saying that this presentation will be on YouTube also. And
Oh, okay.
Anybody who's.
Yeah.
can go find it.
So if I give you the link to the, I can give you the link to the glass tube thing if you want to put that in the whatever in the note on the YouTube video. But it's easy to find if you just go into YouTube and in the search box just put glass tubing with a load of stuff in. Right. Excellent. Anybody else?
It's gonna be interesting to see how you get student experiment blowing glass.
Yeah.
Health and safety.
Yeah. Do we still have to do health and safety? Oh, I typically, when I teach students statistical engineering, I use the famous paper helicopter experiment that George Box used to use. There's a very interesting dimensional analysis solution to that problem as well, and where DA works very well.
There's a glass blowing shop up on North Campus.
Say it.
There's a glass blowing shop.
Excellent. So we could do the case study. Yeah, it would be great because that's like we're turning from paleontology to real work engineering, which would be great. Any other questions?
I have just a comment.
Yeah.
This is excellent to after the fact, to do the root cause analysis. How would an engineer in the current scenario, right? How would they go about not having these type of issues? What would you suggest doing the built-in analysis, kind of thing?
Well, I mean, the first thing you've got to do is ask yourself, do I understand the objective function theoretically? And if you don't, I think one of the things where people went wrong previously is if you don't understand the objective function theoretically, you have to do some experiments. But the really interesting thing is you don't need the objective function; you just need the gradients of the objective function. And so that really makes empirical experiments much more useful. So you don't have to, as long as you can work out the gradients of the objective function experimentally. And you can do that quite easily by just adjusting the noise factors and
Dithering a little bit.
yeah, and then you just measure the gradient numerically. And then you can fit a statistical transfer function to the gradients, and then that will tell you where you're robust. But these days, I mean, if you have to do it experimentally, then engineers these days have got pretty sophisticated computer models, certainly in the automotive space, and I'm sure in other spaces too. They've got pretty sophisticated computer models where these sort of working out the gradients of your objective function should be pretty straightforward, really. And so you can then follow this sort of analysis. But you're trying to turn, to your point about this being after the fact, it's about 60 years after the fact. But anyway, the point is that it's all about turning hindsight into foresight, isn't it? So it's all very well, because we know about this stuff in hindsight, but how do we tell engineers how to do that in foresight? Well, I mean, that's what modern quality engineering or statistical engineering tries to do. And I use this case study as a way to motivate engineers to think this way, because it's quite easy to understand, and the obvious solution, the intuitive solution, is wrong. And so, you say, well, if the intuitive solution is wrong for this, just imagine how your intuition will let you down if you're just about to engineer an autonomous vehicle. Your intuition is probably going to let you down, and so you better do this stuff. Yeah, so that's kind of the picture. Yeah. All right.
Fabulous. Thank you very much.
Okay. Oh, I gotta do it again.